Hello everyone, my name is Colby. I'm an electrical engineer. My specialty is power electronics. And I'm going to start this video series by talking about the types of circuits that you might design. So the first one is analog circuits. And if you are starting off as an electrical engineer, really you can't get away from this one. And the reason for that is every circuit is fundamentally an analog circuit, even digital circuits. Generally speaking, analog circuits will map some kind of a voltage to some other kind of a voltage, or a current to a current, or it can go the other way. You can map a current to a voltage, voltage to a current, you can go either way. Most commonly, an analog circuit will perform linear algebra. Most of the time, analog circuits behave linear. There are, of course, nonlinear circuits. If you're going to design something using discrete transistors, those are quite nonlinear. You have to bias them to the right area. Most of the circuits I design use integrated circuits. I just don't mess with transistors unless I'm talking about power electronics, which we'll get to later. Most analog circuits can be described by just one linear equation. So y equals mx plus b, where m is the slope, b is the offset. It's just algebra. And a bandwidth. The bandwidth you can think of like the highest frequency that your circuit can handle. The highest frequency that your circuit will even look at. Now, this is fundamentally a property of the integrated circuits that you're using. It's also a property of how you design the filters around that IC. For instance, you're almost always going to see some kind of a capacitor on any analog input. And the reason for that is you want to have a nice well-defined capacitance on any analog input. If you have an undefined capacitance, it makes it really hard to figure out what is the bandwidth. Now, just about everything I design is going to be a power converter. That's my specialty, power converters. So, how does analog circuitry show up in a power converter? Well, a big way that it shows up is in the sensing circuits. You know, a power converter has an analog input, an analog output. You need to know what is the voltage on the input. Maybe you need to know what's the voltage on the output. So here is what a voltage sense circuit looks like. This is not the only way to sense voltage. This is just the way that I like to sense voltage. So you start off with a voltage divider, and then you add a capacitor to give it a well-defined bandwidth. Then, almost always, I'm going to use an op-amp in a buffer configuration. And on the output, I'm going to put another filter. This one you might call an anti-aliasing filter. The capacitor in that second filter is going to sit right up against whatever is the analog consumer of this signal. So if that means you have a microcontroller and an ADC, you want that capacitor to go right up against the micro. Another example very quickly is a current shunt amplifier. Sometimes you need to sense the current in various places of your circuit. Well, a current shunt is one way that you can sense that current. A current shunt is just a resistor. That shunt is just another name for a low value resistor. We're talking 1 milliohm, 10 milliohms, something small. And the reason that you might use a current shunt amplifier is because it has very, very good common mode rejection. And it has very good differential amplification. I almost never want to design a current shunt amplifier using an op-amp. Op-amps can be very cheap, yes, but getting the common mode rejection ratio as high as you need it can be very challenging. I've seen a lot of challenges in the past where noise from the common mode pollutes the differential mode signal. And if you're trying to measure some value, generally you don't want it to be noisy. You want it to be a nice clean signal. And the last thing I'm going to say about analog circuits is that they used to be designed quite a lot with discrete transistors. So you would have to know the beta value of the transistor, you would have to know what's the bias you're putting into it, you would have to know all the different configurations of analog amplifiers. I don't mess with that. I just don't mess with that. I use integrated circuits, and most often that's going to look like an op-amp. Next type of circuit I'd like to talk about just briefly is a digital circuit. Digital in this case just means that the voltage tends to go to two states. So you can have your voltage high, or you can have your voltage low. Your logic level might be 3 volts, it might be 5 volts, you might even have 12 volt logic. You can make it whatever you want. Important thing to note with the digital circuit is that whatever is creating that digital voltage and whatever is consuming that digital voltage, they need to be compatible with levels. For instance, you might have a serial data receiver, just something that plugs into your computer with USB. Most of the time, those are compatible with 5 volt logic. If you want one that's compatible with 3 volt logic, so it can actually read a 3 volt signal, you got to make sure you pick one that has a 3 volt compatible input. Now, if you put a 3 volt signal into a 5 volt compatible converter, you're probably going to be fine. You may or may not be able to actually read the signal, but you're probably not going to break anything. If you do it the other way around, if you put a 5 volt signal in something only designed for 3 volts, you may actually damage it. So you have to be very careful when you're selecting voltage levels. That applies to digital circuits. It also applies to analog circuits. Alright, the next kind of circuit I'm going to talk about is power electronics. And this is my specialty. This is where you find power converters. Within power electronics, you find both analog and digital. On the control side, you're going to have a whole lot of analog. You're going to have voltage sensing, current sensing. Your power converter needs to know the state that it's in, and it knows that state by monitoring itself. I guess the first kind of power converter I'd like to talk about is a linear regulator. That looks something like this. It can convert a high voltage into a low voltage, and you need to know that these are very lossy. They tend to create a lot of heat, especially if you load them heavily. These are really only good for low power circuits unless you're willing to just dissipate a whole lot of heat. Sometimes that's acceptable, sometimes it's not. Generally, these are pretty easy to implement. Almost always, you're just going to take the IC straight off the shelf and plop it in your circuit, and there's not too much design work that needs to go into it. You may be designing a feedback network, you may not. Some of them are fixed, some of them have an adjustable output. It really depends which one you buy. I would consider these useful for converting a voltage drop no more than, say, 20 or 30 volts and a current that's really quite small, maybe 10 to 50 milliamps. If you start trying to convert several amps through these, they will get hot, and they just generally don't come in high power versions because of the limitations on power dissipation. You put too much power through them, you're going to cook it, and you might actually break it. So if you want to get higher power, what do? Well, in the 1960s, the requirements on weight and size, especially in the aerospace industry, pushed us to develop something called switch mode power supplies. The big distinction about switch mode power supplies versus linear power supplies is that they operate in discrete states, which sounds a lot more like a digital power converter. And that is one way to describe them. In this case, you'll have something like, say, a buck converter. You might also have a boost converter. Both of these operate by turning a switch on and off. That's all you do. Now you do still need to monitor the process value, the output voltage, the input voltage, but for the most part you're just deciding how long is that switch going to be closed. You close the switch, the current will rise in some inductor, and then you open the switch and the current will fall. That's usually how it works. These can be anywhere from 1 watt up to tens of kilowatts or megawatts. Switch mode power supplies are really modern power supplies. Now, one kind of circuit that you'll see in power electronics that you may not find too much elsewhere is called a gate driver circuit. Most power electronics are going to use big switches. These switches are designed to be turned all the way on or turned all the way off. That is just how they operate. And in order to turn them on and turn them off, you need a gate driver. So what is a gate driver? Well, a gate driver is quite simply a circuit that puts charge on a gate and takes the charge off of the gate. Usually you'll just buy an integrated circuit. These can come in the low voltage or the high voltage variety. You can also have just a simple low side driver, which is the simplest kind. You can have a high side driver, which will typically be isolated, so the second side can just float. And designing these is Not trivial, but once you get the hang of it, it's actually not so hard. Really the big thing is to make sure that you have enough current driving capability, that the voltage input is compatible with your switch, and that's the big stuff. You're going to choose a gate drive resistor that's going to control how fast the switch turns on and turns off. Next type of circuit is audio circuits. Now, this one is actually a subset of power electronics. If you consider a power amplifier, it's going to take a small audio signal and convert it to a big audio signal. It's going to convert something that is line level, or maybe even smaller, microphone level, and it's going to convert that to speaker level. It's going to boost it by several tens of decibels. And ideally, it's going to do so cleanly because you're going to listen to it. Audio circuits have a special requirement on bandwidth. Really, audio frequencies are between roughly 20 hertz and 20 kilohertz. So that's the bandwidth that your circuit is going to respond in. So in the power amplifier circuit, you're going to have essentially a power converter. On the input stage, you're going to have a very sensitive analog input. We're talking an input stage, a preamplifier that can boost maybe up to 60 decibels is common, which is a lot of boosting. Another pro tip about audio circuits is that if you want to have good bass response, generally that requires a very high gain on your input stage. Alright, the last kind of circuit I'm going to talk about is radio frequency circuits, otherwise known as RF, or just radios generally. These are the most wizardly of any electrical circuit that you might see. The reason is, stuff gets weird. You're using advanced physics to hurl some signal off of your board and into outer space. Someone is going to receive it, hopefully. You want to make sure you transmit as little noise as possible because, well, if you're just throwing noise out there, everyone around you is going to hear it. The radio spectrum is shared by all. Here's another example of just how weird these circuits are. The shape of the circuit is significant in the performance of the circuit. For just about any other circuit you design, the shape doesn't matter. But for radio circuits, you have to make sure that everything is laid out very clean. Everything is laid out in a very particular way according to the shape. I am not an RF designer. I just know how weird and wizardly they get. Alright, so to summarize, analog circuits, almost always doing linear algebra. Digital circuits, the voltage is in two discrete states. Power electronics, my specialty. This is where you convert voltage from one level to another level. You can use switch mode power supplies if you want high power, or you can use just a linear regulator if you want something that's simple and easy to design. Audio circuits, it's just a subset of power electronics, and it's used almost always to drive a speaker. And then you have radio frequency circuits, the most wizardly of all. Alright, so that's all I got for you in this video. I hope you've enjoyed it, I hope you found it educational, and I hope that you'll come back and see the next video I put up. Thanks for watching. Bye-bye.